In this video, we're going to look at the basic properties of waves. So this forms lessons 1 and 2 of the GCSE waves topic. So the first thing is, of course, what do we mean by a wave? Right, we can link this back to Year 9 energy transfers. So waves are transfers of energy, right? Really important basic definition, and then a little bit extra for GCSE, without a transfer of matter. Okay, basic definition students must learn. Then you can start to talk about examples of different types of waves. So, we can talk about water waves, we can talk about light, we can talk about sound, we could talk about seismic waves. We can even talk about Mexican waves, which students don't always believe are a type of waves, but they are. They're a transfer of energy without a transfer of matter. And we have people oscillating, people vibrating here as a means to transfer that, rather than the earth, or rather than air, the electromagnetic field, or water particles. You can even get students to wave their hands back and forth, and you can say, well, this is a wave. We're transferring energy, but we're not transferring matter, because the hand is just oscillating backwards and forwards and never actually moves, beyond this small space. And actually, this is a really good way of starting to introduce the basic properties of waves, because you can get students to wave in different ways. You can get them to wave faster, and so you can talk about the frequency of the waves, how many waves per second. You can get them to wave with a greater amplitude, so the hand is moving further from where it originally started, and that is the amplitude. And then we can link that to the other properties of waves, which I'll talk about in a minute. So let's look at two diagrams to show waves. Okay, so this is the typical wave diagram, and we can of course start to label it with the basic definition students need to be aware of. So this black line I've drawn here is the equilibrium line, or it's the line of zero displacement. Okay, so if the wave was entirely along this line, there wouldn't be a wave, because there would be no displacement from the start position. The maximum height of the wave from the equilibrium line, or equally this distance here, is known as the amplitude. And if we go from peak to peak, or trough to trough, so we could go here to here, we could go here to here, or equally we could go here to here as well, this is the wavelength. All right. Peak to peak is a lot easier for students, less likely to make a mistake. But equally, this here is of course a wavelength as well. This type of wave here is known as a transverse wave. Okay, so what distinguishes a transverse wave? The oscillations means vibrations of the particles are perpendicular, so at right angles, to direction of energy transfer. So this wave here is going perhaps left to right, or it could be going right to left, but which way are the particles vibrating? The particles are vibrating up and down. Now, you have to be really clear with this definition: perpendicular to the direction of energy transfer, and that's the vibrations or the oscillations. It's not enough to just say the particles vibrate up and down and the wave goes left to right. That's not enough. A good example of this is a Mexican wave. If you do get students to do this in the class, it's fairly obvious that they are jumping up and down, but the wave is going, perpendicular to that across the class. Other examples of transverse waves: water waves, light waves, one type of seismic wave is transverse, the other is longitudinal. So P waves are transverse and S waves are longitudinal, but that's not GCSE. And then the other one as well that students can mention is a wave on a string. All right, if you want to make a wave on a string or a piece of rope, it has to be transverse. The other type of wave is longitudinal. So we can see the representation of a longitudinal wave here. All right, we've got lines to represent the particles, but equally, you know, we could actually just draw some particles here, and then we would see that they're going to become a lot closer together at these points, and then they start to spread out again when we get out here. So, you know, an example of a longitudinal wave is a sound wave or an S wave. And it's very much, you know, the particles moving forwards and backwards, becoming more dense and more close together, and then spreading out again. So the formal definition, the oscillations or the vibrations of the particles are parallel to the direction of energy transfer or wave motion. So it's not enough for them to say in the same direction, you have to say parallel. Oscillations of the particles parallel to the direction of energy transfer. A good example of this is a slinky. As long as you move the slinky towards and away from you, you can get a really nice longitudinal wave, and you can get it across, you know, the whole classroom if you have a long slinky. So what do we need to be able to label on this wave here? So we need to be able to label the wavelength which is this bit here. Now, this sometimes confuses students, and they'll say, you know, why is the wavelength here, where we're kind of going all the way up, down, and back again, whereas here we're seemingly only going from one point to the other. So it helps to really think about how we match these two types of waves up. So with a longitudinal wave, right, the point of zero displacement is going to be sort of about here and here, right? This is going to be the point of maximum displacement. This is going to be the point of maximum displacement. So if we were to kind of match it up with one of these waves here, right, let's draw the equilibrium line. It's going to be something like this here. All right, so we've got our trough, or you know, it could be our peak as well. We could shift it so that this is our wavelength, like this. Right, this point here, zero displacement, is important. How else could we label these diagrams? What else comes up? Well, we've got points where it's really, really spread out. These points here. These are known as rarefactions, which is not a word we use very often, but that is the formal term. And then the points where everything is close together or bunched up, these are compressions. And then on our transverse wave, we could talk about peaks or crests. We could also talk about troughs here. And then importantly as well, if we had our graph and we labeled our axis time rather than, I guess this would be distance, then we wouldn't be labeling wavelengths, we would be labeling time periods. Okay, the time period is the time for one complete wave. And then we need to obviously know the relationship between time period and frequency. So time period is simply 1 over frequency. So this makes a lot of sense when we talk about units. So we've got seconds is equal to 1 over hertz. And of course, a hertz is the unit of frequency, and this is equivalent to per second. So how many waves per second? So it should be fairly obvious that, you know, 1 over the time period is the frequency. And then the final thing that's worth mentioning is the relationship between speed and frequency and wavelength. So the speed of a wave is equal to its frequency times its wavelength. V is F lambda, that's the Greek symbol lambda. If we're talking about light, then we use this form where c is the speed of light, which is 300 million meters per second. It's obviously very high. If it's a regular wave that's not light, then we use v for velocity. It's not immediately obvious to students why this is true, so it's worth convincing them. What are the units of speed? The units of speed are meters per second. Okay, what is the unit of wavelength? Well, it's the length. So we're measuring a distance, we use meter. What's the unit of frequency? It's hertz. What does hertz mean? It means per second. So it should be fairly obvious that if you get meter and you times it by per second, you've got a speed. This is a really nice, proof, I guess. You can do a really nice demonstration with this. You can get two students walking across the classroom, and you can get one student that has a really long stride, so a really long wavelength, and they'll obviously be, the rate of their steps is quite slow, and then you'll have another student that's going to take really short steps, and in order for them to stay the same speed, what has to happen? They obviously have to have a much higher rate of taking these steps, so the frequency goes up as the wavelength goes down. There's also a really nice GIF that shows exactly this for light, which will be on the PowerPoint for this lesson as well.